So our next topic is Jordan canonical form. Canonical form. Jordan canonical form. Now, what is a canonical form? Chapter name also says canonical forms. So, what is a canonical form? We want see a matrix A is given. We want to convert this matrix into a simpler form. Best is we want to convert it into a diagonal form. If it is not, if it cannot be converted into a diagonal matrix, then we want to convert into a matrix which is short of diagonal matrix. Short of diagonal matrix means it is not exactly diagonal matrix. See, what happens is when you have a diagonal matrix, then you have a diagonal, all other parts are zero. When you have a triangular matrix, then you have at least one part is zero and the other part is anything which doesn't matter to us. Now we want to convert, so this thing is called short of diagonal matrix. Okay, so you say if the matrix can be converted into diagonal matrix, then it is best. Otherwise, you convert it into a triangular matrix, you convert it into Jordan form, you convert it into rational canonical form. Okay, so this is the thing. Now, first of all, we should understand that what is a Jordan form. So we need to understand this is a definition Jordan block. What is Jordan block? A Jordan block looks like, for example, this is a Jordan block of order 1 cross 1. Then you have a Jordan block of order 2. You have lambda lambda on diagonal. On super diagonal you have 1 and the lower portion will always be 0. This is a 2 cross 2 block. You have lambda lambda lambda. On super diagonal you have 1 1 and then your lower part will always be 0, and this is the Jordan block of order 3. You have a Jordan block of order 4. For example, this is diagonal. Super diagonal means a diagonal above the main diagonal. So 1 1 1 on this, and then all other entries are 0. All other entries are 0, like this. Okay. In the same way, you can say that you have, this is a 4 cross 4. Then you say Aij. Then you say this is n cross n, and this is a Jordan block. First thing is AII. AII means your main diagonal. Okay, on main diagonal you will be having lambda. Fine. Then A, for example, this is A11, this is A12. I hope you understand this. Then AI and I plus 1. This will be 1. Then all other entries Aij is equal to 0 elsewhere. So diagonal entry will always be 1. Diagonal entry will always be lambda. Super diagonal will be 1 and all other entries will become 0. If you see this thing is called Jordan form. Now what is Jordan canonical form? Jordan canonical form is a matrix which consists of Jordan blocks only in direct sum form. So for example, you have J1, then J2 up to so on Jk. This is your matrix. Okay, this is your matrix. So this is a Jordan canonical form. For example, I represent, for example, you have 1. Okay, you have 1. This is Jordan block of order 1. Fine. Then you have, for example, 2 2. For example, like this. This is again a Jordan block. You have, for example, 5 5 5 1 1 0 0 0 0 in this way. So you see that you had a 6 cross 6 matrix and you converted that matrix into Jordan. This is Jordan canonical form in which you have only Jordan blocks. You have Jordan block, all other entries are 0. So this is a 6 cross 6 matrix. Somehow you converted that 6 cross 6 matrix into this form. Okay, I hope this thing is clear to you. Okay, so our next part is actually a numerical format, algorithm to convert or transform matrix to its Jordan canonical form. This is our new topic. Now, what I will do is I will write one question, one numerical, and the algorithm simultaneously, and you will not find it difficult. So, a 3 cross 3 matrix is given to us. For example, the matrix is 0, 4, 2, then minus 3, 8, 3, then 4 minus 8 minus 2. This is a matrix, this is given to us. See, the only difficulty in this method is the matrix multiplication involved. So many matrices you have to multiply, you have to find rank, so and so and so. And when you are multiplying matrices in one way or the other, you do only one mistake and the question will be wrong. Okay, so this is the only difficulty in this method, otherwise there is nothing in it. Now, step one, find eigenvalues. So step one is find eigenvalues. I find its eigenvalues. When I find eigenvalues come out to be 2, 2, 2. For this matrix, eigenvalues come out to be 2, 2, 2. Fine. Now what we will be doing is we will be finding a minus 2i, and then we will be finding rank of a minus 2i. Then we will find a minus 2i square. Then we will find a minus 2i the square rank. I will write here step 2. When you have eigenvalues, let lambda be the eigenvalue. Let lambda be eigenvalue. When you have eigenvalue, what you will do is you will say a minus lambda I and then rank of a minus lambda I. Second is a minus lambda I square and then rank of a minus lambda I square. Then a minus lambda I cube and then a minus lambda I cube's rank, up to so on. You have to do this up to, for example, I say you have to do this up to r minus 1, and you have to find rank of a minus lambda I or r minus 1. When you stop at that stage when you find the rank of these matrices a minus I, a minus lambda, a minus lambda I, a minus lambda I square up to so on. You stop at that stage, I mean r. At what power you will stop? A day will come when a minus lambda I par r minus 1's rank and a minus lambda I par r rank will become equal. When the ranks become equal, then you will stop. Okay, so for this matrix capital A, you have a minus lambda I. Now this portion you obviously you will have to do by yourself. You have a minus lambda I, a minus 2i. You find its rank, and the rank come out to be 1. You find a minus lambda, a minus 2i's square. You find the rank, and it becomes 0 because this matrix is itself 0. A minus lambda I square is 0. If a minus 2i square is 0, then a minus 2i cube will also be equal to 0. What I am trying to say is its rank will also be 0. Okay. So the thing is, you will stop at, you know that you will stop at that stage when you find that you are taking powers but rank is not changing. Here the rank, obviously the least possible value of rank is 0. It is 0, it cannot decrease further. Okay, so you say that at what power you find the stability in the rank. So you say therefore S is equal to 2. Okay, here you say therefore S is equal to R minus 1. Okay, fine. Now next thing is you will find Q1, Q2, Q3 up to so on. Here you have Q1, Q2 up to so on. For example, Q1 is 3 minus rank of A minus 2i. So what is 3? What is this 3? 3 is order of matrix. So for example, in this algorithm, if we are writing for a n cross n matrix, then this Q1 is n minus rank of A minus lambda I. Then rank of A minus lambda I minus rank of A minus lambda I square. Then rank of A minus lambda I square minus rank of A minus lambda I cube. Up to so on QR. Okay, up to so on QR, you find this. When you find, you will find row of A minus lambda I power R minus 1 minus row A minus lambda I power R. So you have row A minus 2i minus row A minus 2i whole square. Q3 is row A minus 2i square minus row A minus 2i whole cube. So this thing is 3 minus 1 is equal to 2. This thing is 1 minus 0 is equal to 1. Then obviously 2 and 3. Last value, this value will always be 0. This value will always be 0. Okay, so I think this much is clear. So I will repeat the whole procedure. First is you have a matrix, find eigenvalue. Done. Then find A minus lambda I and its powers and their ranks. At some stage, rank will stabilize. The stage at which rank will stabilize will give you the value of S. Then you find Q1, Q2, Q3 up to so on. Now, last step. Last step is corresponding to eigenvalue lambda is equal to 2. Jordan canonical form of capital A will have, okay, Jordan canonical form of A will have. So here I will write corresponding to eigenvalue lambda, Jordan canonical form of A will have, okay, will have what should I write? Will have Q1 minus Q2 blocks of order 1, Q2 minus Q3 blocks of order 2 up to so on up to so on, Q R minus 1 minus QR, okay, blocks of order R minus 1. Here what you have? You have corresponding to eigenvalue lambda is equal to 2, Jordan canonical form of A will have Q1 minus Q2 means 2 minus 1 is equal to 1 blocks of order 1. Jordan blocks, sorry. Jordan blocks of order 1. Of order 1. Again, Q2 minus Q3 is equal to 1 minus 0 is equal to 1 Jordan block of order 2. Fine. Hence JCF of capital A is given by, I hope this thing is clear to you, is given by Jordan canonical form of A is given by, you say that what is eigenvalue? Eigenvalue is 2. And the eigenvalue say that it will be having one block of order 1. One block of order 1. So this is 2. Order 1 block means single element. Then order 2 block. Order 2 block is 2, 2, then 1, then 0. All other entries are 0. Therefore, Jordan canonical form of A is given by this. This is your answer, and this is a 8-mark question. Believe me, I have not done this step. This is the main step. When you find A minus 2y, then you have to find the rank. It takes time. Then you have to find A minus 2y square. Square means multiplication of two matrices. So obviously you can understand that this takes time. So the only difficult part in this method is the calculation. Further, you can see that in this question there was only one eigenvalue 2, 2, 2. In most of the problems you have more than one eigenvalues, the distinct eigenvalues, for example 2, 3. So you will have to do the whole procedure, whole algorithm for 2 as well as for 3. Okay, so I will do another example in which we have two type of eigenvalues. So numerical is A is equal to 157, then 043, then 001. So you see this is already in triangular format, and obviously this question will always be in Jordan form only. You cannot say that you convert it into triangular form because it is already a triangle. Now, but this thing gives us eigenvalues directly. So you need not find characteristic equation and all. You can directly say that eigenvalues are 1, 1 and 4. Clear to you? Then you say for lambda is equal to 1. Okay, for lambda is equal to 1. You find A minus I square, so and so and so. Find its rank. When you find rank of A minus I, you will see that its rank is 2. Then you find rank of A minus I whole square. You see it will be equal to 1. Then you find rank of obviously A minus I cube, and you find rank, it will be A minus I cube's rank will be 1. So obviously S is equal to 2. The stage at which we stop, at which the rank do not change, gives you S. Now you want to find Q1, Q2, Q3 up to so on, but we will stop at Q3 only. So this is First is Q1. Q1 depends on order of matrix. So this is 3 minus row of A minus I. Then row A minus I square. Then row of A minus I square, A minus I cube. So this is 3 minus 2, this is 2 minus 1, this is 1 minus 1. So 1, then 0. Clear to you? Okay? Believe me, it will take time to calculate these things. The only thing is, when I am doing this question, I am writing these things directly. This is the only thing on which you have to spend time doing matrix multiplication and finding ranks. Okay, so you have this thing now. Now, therefore, lambda is equal to 1 will have q1 minus q2 is equal to 1 minus 1 is equal to 0. Jordan blocks of order 1 done, comma q2 minus q3 is equal to 1 minus 0 Jordan blocks of order 2. So for lambda is equal to 1, done. Highlight this thing, okay, and move forward for lambda is equal to 4. Now you have lambda is equal to 4. When you have lambda is equal to 4, you say a minus 4i. Okay, a minus 4i. When you find a minus 4i, you find its rank. Its rank will be equal to 1. Then you find a minus 4i square, you find its rank. It will also be equal to 1. A minus 4i square. Its rank will also be equal to 1. So at which stage the rank stabilize? At first stage only. S is equal to 1. Now you say that Q1 is, Q2 is. Okay, Q1 is and Q2 is. So Q1 is like 3 minus row A minus 4i. Then Q2 is row A minus 4i minus row A minus 4i whole square. Clear to you? So this is 3 minus rank is A minus 4i's rank is 1, so this is 2. And then Q2 is, this is 1 and this is 1, so this is 0. Done. So therefore last step, therefore lambda is equal to 4 will have, okay, will have Q1 minus Q2 is equal to 2 1 second please. Okay, so this rank is 2 and this rank is also 2. Sorry, a minus 4i's rank is 2, a minus 4i square rank is also 2. So this is 2. When 3 minus 2 is, this is equal to 1. And then you have 2 and 2. So this is 2 minus 2 is equal to 0. And then last step. Therefore lambda is equal to 4 will have q1 minus q2 means 1 minus 0 is equal to 1. Jordan block of Jordan block of order 1. Okay, now last step is hence Jordan canonical form of A is given by. Now you ask lambda is equal to 1, what he needs, and for lambda is equal to 4, what he says. Lambda is equal to 1 says that 0 blocks of order 1, no block of order 1, only one block of order 2. So one block of order 2 means 1 1 1 0. Okay, in diagonal you have eigenvalues. Below the diagonal all 0. Above the diagonal one super diagonal will be 1. All other will be 0. We have only one entry here, so it becomes 1. It is done. Next is you have lambda is equal to 4. When you have lambda is equal to 4, you find its Jordan block, and it says that only one block and is of order 1. So obviously you have a 3 cross 3 matrix. Two places are already filled. Obviously only one place is vacant. So this is 4. Okay, so is the required Jordan canonical form. I hope this is clear to everyone. This is very easy. So next numerical is a 16 marks numerical. Obviously this is a 4 cross 4 or even 5 cross 5 matrix. Mostly in our syllabus, they will, from your past experiences, we have seen that there will be at most a 4 cross 4 matrix. Okay, so the matrix is given to be 5 minus 5 1 minus 2 4, then 0 5, then 2 2, then 0 0 5, and then 3, then 0 0 0 and 4. So this thing is given. Now what happens is, this is a triangular matrix. Eigenvalues are 5 5 5 and 4. Then you find a minus 5i, a minus 5i square, find its rank, then find its rank. When you find ranks, the ranks comes out to be, when you find these ranks, the ranks comes out to be, this is 3, then this is 2. It is changing. You have to find 5 minus I cube also. When you find rank, it is 5i whole cube. So the rank is 1, again changing. So you have to find power 4 also. So this is a minus 5i power 4. When you find, it is 1. So finally it stabilizes. So you say this is s is equal to 3. S is equal to 3. So you have to find Q1, Q2 and Q3. So first is Q1 is 4 minus rank of A minus 5i. Then row 5i minus 5i square. Then row 5i square minus 5i cube. Then row 5i cube minus 5i 4. Many people ignore this q4 also because they know that it will surely be 0 1. So this is 4 minus 3, this is 3 minus 2, this is 2 minus 1, this is 1 minus 1. Okay, so this is 1, this is 1, this is 1, this is 0. Now last step. Therefore for lambda is equal to 1, q1 minus q2, q2 minus q1 minus q2, q2 minus q3, q3 minus q4. Okay, Jordan block of order of order 1, 2, 3. Okay, ji. So values are 1 minus 1, 1 minus 1, 1 minus 0. So this is 0, this is 0, this is 1. Jordan block, Jordan block, Jordan block. So you say that it will be having, therefore Jordan canonical form of A will have one Jordan block of, corresponding to lambda is equal to 5 of order 3. 3 orders, only one Jordan block will be there. Done. Next is lambda is equal to 4. So you have lambda is equal to 4. You find the rank for A minus 4i. When you find the rank, this rank comes out to be 3. This rank comes out to be 3. A minus 4i square also ranks comes out to be 3. So in very first stage the ranks stabilize. Okay. Now you have S is equal to 2. S is equal to 2 or S is equal to 1? At what? Sorry, S is equal to 1. Sorry. You have S is equal to 1. So you say this is Q1 and this is Q2. This is 4 minus, this is row of A minus 4i. This is row 4 minus, sorry, A minus 4i minus A minus 4i square. So this is 4 minus 3 and this is 3 minus 3. This is 1, this is 0. Therefore, for lambda is equal to 4, sorry, lambda is equal to 5. For lambda is equal to 4, Q1 minus Q2 means 1 minus 0 Jordan block of order 1. See, we should understand that we have a 4 cross 4. We have a 4 cross 4 matrix. 3 places will be taken by 5 and obviously only one place will be left for 4. So we are doing this step, but we know that whenever we will do, for in last example also this occurred, when we will do, we know that it will look like a Jordan block of order 1 for the eigenvalue that occur only once. Okay, so hence Jordan canonical form of A is given by, okay, Jordan canonical form of A is given by 5, 5, 5. You need a Jordan block of order 3. Below diagonal all entries are 0. Above diagonal one super diagonal which have 1 and all other entries are 0. So this is your Jordan canonical form for A. So this is a 16 marks question, because see, this is of 16 marks only because this is a 4 cross 4 matrix. Or if a paper of a difficult pattern comes in your exam, then it will be of 12 marks. Okay, but not less than this. If it is a 3 cross 3 matrix, then it is a 8 mark question. Okay, and when it is a 12 mark question, then a 4 mark question, then a 4 mark theorem of very easy nature will appear along with. Okay,